So we've been digging through a stack of documents today that honestly, it fundamentally changes how you look at a Tesla.
It really does.
You think you're looking at a car, but these architecture diagrams, I mean, we're actually looking at a server-class compute node on wheels.
It's a complete category shift. And what's so striking in these sources isn't just, the raw speed, it's the constraints. This whole evolution is really a story about fighting physics.
Fighting physics.
Yes, specifically thermodynamics and this thing called the memory wall.
Okay, let's start with that first fight then.
Mhm.
The sources take us all the way back to hardware 2.5.
Right. This was the Nvidia Pascal era.
Yeah.
And on paper, these were powerful chips.
Powerful for a server farm, maybe.
Exactly. But the batch size 1 problem just killed them in a car.
And this is that critical latency thing, right? In a data center, you can bundle a bunch of images into a batch and process them all at once. It's efficient.
But you don't have that luxury at 65 miles an hour. You need to process a single frame, one frame, the instant it comes in.
Because if you wait even a fraction of a second,
The car's already traveled, 10 feet, blind? The Nvidia chips were built for throughput, not that instant reaction time.
the analysis also says they were over-precisioned.
Yeah, they were using floating point math. It's basically a scientific calculator when all the neural nets really needed was simple integer math.
So like using a graphing calculator for simple addition.
Perfect analogy. It works, but you're just wasting so much energy generating all this useless heat.
And that inefficiency, that's what pushed them to design their own silicon with hardware 3.
The famous FSD computer. And the big win there wasn't just we made it ourselves.
It was the memory.
It was placing 32 megabytes of SRAM right on the die. That is the key.
By keeping the data right next to the processor, it solved that latency problem.
It did. But as the software got smarter, they ran headfirst into the next problem, the memory wall.
Because the AI models themselves changed. We're not just doing image recognition anymore. We moved to transformers.
The same architecture that's behind stuff like ChatGPT. And transformers are just incredibly data hungry. Hardware 3 used LPDDR4 memory, which is efficient, but the pipe was just too narrow.
It couldn't feed the neural nets fast enough.
The processors were literally sitting there, idle, just waiting for data.
Which brings us to the current generation, hardware 4. The sources describe this as almost a brute force solution.
It kind of is. To smash through that memory wall, they just switched to GDDR6 memory.
The kind of high-performance stuff you'd find in a gaming console.
And it tripled the bandwidth. We're talking nearly 400 gigabytes per second.
And they needed that for the new 5-megapixel cameras for the high-def Phoenix radar.
Right. But it comes at a huge cost. GDDR6 runs hot, really hot. The philosophy shifted from maximum efficiency to just maximum data flow.
And if you think HW4 is hot, these projections for AI5, the one for maybe 2026, they're terrifying.
We're seeing estimates around 800 watts of power draw.
800 watts. For context, that's a high-end gaming PC running at full blast, but it's tucked inside your dashboard. You can't cool that with a fan.
No way. The specs basically imply liquid cooling. It has to be integrated right into the car's main thermal loop. So you're essentially driving a data center rack.
And all that power opens up that wild distributed inference fleet concept.
Which is the part that sounds like pure sci-fi.
100 million cars, all parked and plugged in, acting as a single 100-gigawatt supercomputer.
So while you sleep, your car is helping train the next AI. It's a fascinating use of idle hardware.
But it leads to a really difficult reality for anyone who actually owns one, doesn't it? The bifurcation.
That is the elephant in the room.
HW3, HW4, and AI5 are physically incompatible. You've got different power, different cooling. You cannot just swap the chip.
It's not a simple upgrade. Not at all.
So here's the thought. If the memory wall is real, and modern AI really does need the bandwidth of HW4 or the raw power of AI5, where does that leave the millions of hardware 3 cars on the road today?
It suggests they might hit a hard ceiling on how smart they can actually get.
A sobering thought for early adopters. We've gone from modified graphics cards to liquid-cooled supercomputers in a decade, but the hardware legacy might be the biggest hurdle left. That's it for this deep dive. Drive safe.